Hey everyone, we got this problem here, this free response problem from 2012. And so it says, we got this person pushing this box here. It says, beginning at time 0, a student exerts a horizontal force on a box of mass 30 kilograms, causing it to move at 1.2 meters per second toward an elevator door located 16 meters away as shown above. The coefficient of kinetic friction, UK, between the box and the floor is 0.2 there. So first thing we want to do here is draw a free body diagram, labeling all the forces on the box. So we've obviously got the force of gravity acting down on the box, and then to an equal amount, we've got a normal force acting up from the floor. We know these two have to be equal because the box isn't accelerating up or down. Then we've got an applied force from the student to the right, and then we'll have an equal amount of friction force back to the left. We know these two have to be equal because it's going a constant 1.2 meters per second across the floor. So that lets us set up our next part here. Now that we've got our free body diagram, on this part, they are saying, calculate the magnitude of the horizontal force the student must exert in order to keep it moving at 1.2 meters per second. Don't add anything to your free body diagram. You'd have to draw it somewhere else here. Okay, here's the thing. The velocity is constant. That is what they tell us. And another way to say that is that the acceleration is 0. And if that is true, that is saying that the sum of the forces is equal to 0. By the way, that's true in the x, and the sum of the forces must be true in the y, because this thing isn't accelerating horizontally or vertically. So now we can start to set this up. In the x direction here, we can write this. The sum of the forces in the x direction is 0, but what else is it equal to? It's the applied force to the right minus the friction force back to the left there. We know that those are equal to 0. We also know then basically that the applied force must be equal to the force of friction there. And furthermore, we know the force of friction is defined as the coefficient of friction times the normal force. So now another thing that we know is in the y direction. So if we can now find the applied force if we just find the friction force, which is just mu times the normal force. So let's go get this normal force. For that, we've got to look at the y. The sum of the forces in the y direction is the normal force up minus the force of gravity down. Those two also add up to be equal to 0. So what that basically means is our normal force must be equal to our weight. So now we can plug basically our weight in for our normal force here. So finally, our applied force is equal to our force of friction, which is mu times the force of gravity. So let's plug that in. Our applied force is our coefficient is 0.2, and our gravity, since it is a 30 kilogram box, it weighs 300 newtons. And so you will wind up with 60 newtons of applied force. Technically, what we found was that the friction force had to be 60 newtons, but the applied force must also be equal to 60 newtons in order to keep everything balanced there. All right, so let's move that out of the way, and now let's bring this one in. Now, this one winds up being a fair amount of work. It says after 4 seconds, the elevator door opens and stays open for 5 seconds. The student immediately exerts a larger force on the box, and the front of the box just reaches the elevator door as it starts to close here. So here's the thing. A new force means we will have a new acceleration, and we have to do this in 2 parts here, 2 separate parts to solve it. Now, when you go to start to look for the force, you may think that the sum of the forces is equal to mass times acceleration, and that is correct. The problem is, if we're looking for the applied force as an unknown inside of this, but we don't know the acceleration either, so we can't set up anything to solve for this. So what we're going to have to go and do first is to find the acceleration. How are we going to do that? We're actually going to have to turn back towards kinematics to solve this one here. And to make it more difficult than that, we've got two separate sections here. So we were going to constant speed. So we can use the third equation for its constant speed version. In other words, the distance we go is just our velocity times time. We're going to have to solve for that and then solve for the final part when we're accelerating. This is pretty straightforward. We were going 1.2 meters per second, and we did that for 4 seconds. So that means we covered 4.8 meters before we even began to accelerate. If we look at the problem then, when we go to find our acceleration, we had to cover a total of 16, but 4.8 of that was already covered in the constant speed part. So we do 16 meters minus 4.8 meters, and that leaves us with 11.2 meters to cover while we are accelerating. So now let's think about what we know. We know we've got to cover a distance of 11.2 meters. We know we are looking for our acceleration. We know that our initial velocity in the x direction is 1.2 meters per second. And we know that we've got a time of 5 seconds to get there. So what equation talks about displacement, acceleration, initial velocity, and time all at once? That is the third equation. So delta x equals v0x times t plus 1/2 a t squared. We're looking for acceleration here, so I'm going to go ahead and solve all of this equation for acceleration. It's going to equal then delta x minus your initial velocity times time, all of that divided by 1/2 t squared. I just did all that algebra in one step there. Now we've got to plug in for each of these values that we know. We know the distance we've got to cover is 11.2 meters, not 16. Subtract from that our initial speed of 1.2. The time is 5 seconds to cover that. And then that is all divided by 1/2 times our time squared. So if you are careful with all of that, you will get that that acceleration is 0.416 meters per second squared. So now we know our acceleration, and now we can plug it into here and start to solve for this new force. But first, let's write this out. Let me expand out the sum of the forces. We have this new force, this new applied force, minus the force of friction back the other way, is equal to mass times acceleration. So that means our new applied force is equal to mass times acceleration plus this force of friction. I added it to the other side. Now we know every single one of these. We can substitute in and solve. So our mass is 30 kilograms. Our acceleration, we just found right here, is 0.416. We're going to add that to our force of friction. We don't even have to go back and find a new force of friction because kinetic friction is constant. So the force of friction is still 60 newtons. And when you go and add all of that up, you will get 72.48 newtons is our new force to accelerate that much. All right, almost done there. Now in the last part right here, they want an acceleration versus time, a velocity versus time, and a position versus time for this situation here. Notice they added 4 and 9 seconds when we begin to accelerate and when we reach the door. So at first we had no acceleration, and then we jump up to some value right there. Now you don't have to label the side, but we know what this value is. It is 0.4, what did we say it was? 16. So that's that value there. What about velocity? Velocity was constant up to 4 seconds, and then we began to accelerate. And we know, we don't have to label this again, but we know what this is. That's 1.2 meters per second. And then finally, position. We were going a constant speed, which will look like this up to 4 seconds, and then we begin to accelerate, so we will start to have a parabola.